let's move on to odd functions. I've drawn one here, and I ask you, what do you notice?
Well, it looks similar, the left and the right, but it's not the same type of symmetry. It seems like it's a reflection and then some sort of inversion.
Yeah, indeed. So you could think of it as a double reflection. So first in the y-axis and then in the x-axis, if you like. You could think of it that way. It's probably the easiest to think of it as a rotation about the origin of 180 degrees. Okay, so what does that mean? It means like, okay, if we drew circles centered at the origin, and I'm testing my drawing capabilities. Wow, they're pretty bad. But imagine that's a circle with a constant radius. Then this line should go right through the origin. So obviously I did not do a very good job. I should have drawn the circle more like something like that. Okay, and then this line should go through and hit at this point and here. So it looks like a rotation. So any point that you take here, you should rotate it 180 degrees, and it should give you another corresponding point there. So you take the same distance to this point and the same distance to that point. And I did a little bit better job here, although this squiggly up here doesn't look too impressive. Okay, so now maybe let's clean this up a little bit, and then let's take a look at what we can say about this more from an equation point of view. So let's take some specific points. So f of minus 1. So if we take f of minus 1, well, this is minus 1 here. So f of minus 1, well, that has the value of 1. And if we then look at f of 1, so this is 1, that has the value of minus 1. So f of minus 1 is 1, and f of 1 is minus 1, so 1 is equal to minus f of 1. So we have f of minus 1 is equal to minus f of 1. Let's take again a look at the root, which just happens to be at minus square root of 2, which is here. So that's equal to 0. And we still have this other root here, which is at plus root 2. Okay, so then this is equal to f of the square root of 2. And let's take a point in between. So let's take a point at 1/2. So this is about 1/2, and we take a look at the value of that. So f of 1/2, and by very careful inspection, I can see that that's 7 over 32. No, actually, it's because I know the equation for this graph. That's why I know it's equal to 7 over 32. And if we take f of at 1/2, well, it's going to give us the value of minus 7 over 32. So we have minus 1/2 is equal to minus f of 1/2. And this is how we define odd symmetry. F of minus x is equal to minus f of x for all x in the domain. So it's repeated here in this definition. So f is odd if f of minus x is equal to minus f of x for all x in the domain. Notice again, just like in the evenness, implicit in this is because we have to evaluate f both at x and at minus x. So what we need is x is in the domain implies minus x is in the domain and vice versa. And once again, we could restrict the domain so that that's true. So once again, there's a value for graphing in that we could carefully graph the left or right side and then rotate it around. So we could just focus on trying to get a good graph of this right side, and then we could just rotate all the points around to get the left side, or vice versa. So now we can go and look at this actual equation for that function, and that was x to the 5 minus 2x cubed. Notice there's no even powers. Even powers of polynomials correspond to even functions. This only has odd powers. And we can make this statement, which is later established when we divide functions into even and odd parts, is that if f is a polynomial, then it's odd if and only if it only has odd powers. So it can't have a constant except for 0, because x to the 0 is even. It's an even power. 0 is an even power. Now it's time for another question. Suppose f is odd. What is the value of f of 0? Assuming, of course, that 0 is in the domain.
Well, if f is odd, then I know that f of 0 should be f of minus 0. That doesn't really make too much sense. Maybe it's just a special case?
Well, actually, f of 0 has to be 0. Let me try to explain it. If f is odd, f of 0 has to be 0. It has to pass right through the origin. So let's first think about this as a rotation. So if you're starting right at x0 and you rotate 180 degrees, the only way to stay within that rotation would be to be right at 0. But let's do this using this property. By the property of oddness, that f of minus x is equal to minus f of x, with x being equal to 0, we find that f of minus 0 is equal to minus f of 0. That's by oddness. However, we also know that minus 0 is equal to 0. That 0 is the only number that is itself its additive inverse, meaning minus 0 is equal to 0. And so f of minus 0 is also equal to f of 0. And so when you put these two things together, what you have is you have minus f of 0 is equal to f of 0. The only way that can be true is if it's equal to 0. So f of 0 has to be 0. Let's move on to a non-polynomial example. Here is sine. Is sine odd? Before we explained that cosine was even, so maybe sine is odd. Well, what we can do is we can take points. So again, we could look at different values. So let's look at the value when x is equal to 5. Okay, so now if we look at f of minus 5, it should give us the negative of that value. And it looks like it does. Let's take another example. Let's take f of minus 1. So if we look at f of minus 1, all right, then if that should give us negative the value of f of 1. And it looks like it does. All right, so testing a couple of points, it looks like this is satisfied. Once more, it looks like this is a rotation. If we take this right side and we rotate it 180 degrees, it does look like we get the left side. So it does look like a rotation about the origin of 180 degrees. So yes, it is in fact odd.